Hello and welcome to Physics with William. This is the place where curiosity is the constant and science provides the route for exploration. Today, we're about to embark on a journey that goes beyond the boundaries of what we know. A journey into the very fabric of the universe, where something unexpected might be waiting just around the corner. Imagine a world where the rules we thought were set in stone no longer seem to fit, where familiar forces and constants are challenged by strange anomalies, inviting us to rethink everything. That is exactly where we find ourselves today. The possibilities, they stretch far and wide, and all of this is centered around a recent discovery that could change our understanding of the universe forever, the idea of a fifth force. But before we dive into the depths of particle physics and the experiments that brought us here, let me first ask, where are you listening from right now? What time is it in your corner of the world? I always find it interesting how time, this invisible force, shapes our perceptions of reality. And just as time constantly ticks forward, we too find ourselves moving toward new discoveries, pushing the boundaries of knowledge. If you find this exploration intriguing, a little thought-provoking, or perhaps even calming in its own way, consider liking the video and subscribing to Physics with William. This helps our little community grow and ensures that more curious minds like yours find their way here, joining us as we delve into the mysteries of the cosmos. Now, let's begin. If you've ever wondered about the forces that govern our universe, you probably know the basic ones already. Gravity, electromagnetism, and the strong and weak nuclear forces. These four forces shape everything we experience, from the way we move on Earth to the behavior of particles far, far away. But what if I told you that scientists have recently uncovered something that could suggest there's a hidden force, one we've never detected before? A fifth force that could change everything we know. This is where the real story begins, and it all starts with two seemingly unconnected experiments. The Muon G2 experiment and the anomalies at CERN's LHCb experiment. The Muon G2 experiment involves a very specific particle, the muon, which is essentially a heavier version of the electron. We know from previous research that the muon has an interesting magnetic property. When subjected to a magnetic field, it behaves in a way that should follow certain rules established by the standard model of particle physics. But in 2021, something strange happened. The results of the experiment didn't quite match what physicists expected. The muon's magnetic moment seemed to be off, pointing to something more than just the forces we currently understand. This anomaly was subtle, but profound. Could it be pointing to a new interaction, perhaps a fifth force? Meanwhile, at CERN, another set of experiments at the LHCb, Large Hadron Collider Beauty, experiment revealed an unexpected pattern in the behavior of B-mesons, a type of subatomic particle. These particles should have behaved in a certain way, but instead their interaction seemed to defy the laws as we currently understand them. This anomaly also hinted at something beyond the established four forces. The results from both of these experiments, while coming from different particles and different setups, seemed to point to a similar conclusion: the possibility of an unknown force at work in the universe. But before we get too excited about the prospect of a fifth force, we need to take a step back and think about what such a discovery could mean. What would it look like? Could it change the way we understand everything from gravity to the forces at the quantum level? And more importantly, how do we even begin to investigate such an elusive entity? That's where we are now, at the edge of a new frontier in physics. These anomalies are not just small quirks in the data, they represent something much bigger. They're calling into question the very structure of the standard model. And as we dig deeper into the nature of these results, we start to consider that we might be living in a universe that's far more complex than we've ever imagined. So what is this new force? What role does it play in the vast cosmic dance of particles and forces that shape our reality? Let's take a closer look at the fundamental forces that govern our world and begin to imagine what a fifth force might bring to the table. As we continue this exploration, let's keep in mind that what we're dealing with is not just a discovery, it's a potential turning point in our understanding of the universe itself. The hunt for this fifth force may lead us down paths we can't even begin to predict, and yet that's the beauty of science. We may not have all the answers yet, but every question we ask brings us one step closer to understanding the nature of reality itself. Now, let's dive into the first aspect of this discovery, understanding the four known forces that have shaped our understanding of the universe for centuries. It's only by revisiting what we know that we can begin to understand what lies beyond the horizon of the known world. For centuries, humans have looked up at the stars, gazed at the horizon, and pondered the forces that shape the world around them. From the ancient Greeks who theorized about the natural elements to the scientists of the modern era, the search to understand the forces of nature has been a fundamental part of our quest to comprehend the universe. But what exactly are forces, and why are they so central to our understanding of reality? At the most basic level, a force is simply something that causes an object to move or change its state. It can make a ball roll down a hill, an apple fall from a tree, or the Earth orbit around the Sun. Forces are responsible for the very existence of motion, structure, and change in the universe. Whether we're dealing with a massive planet or a tiny particle, the effects of forces are felt in all corners of the cosmos. Over time, scientists have identified four fundamental forces that govern the behavior of everything in the universe. These are the forces that shape everything from the orbits of planets to the interactions between atoms and subatomic particles. Let's take a look at each one in turn. The first and most familiar force is gravity. Gravity is the force that pulls objects toward each other. It's what keeps the Earth in orbit around the Sun, and what causes objects to fall toward the ground when dropped. Despite being the force we feel most directly, gravity is also the weakest of the four fundamental forces. However, it's the one that has the most far-reaching effects, shaping the structure of entire galaxies and the movements of stars, planets, and moons. The force of gravity depends on the mass of the objects involved. The more massive the objects, the stronger the gravitational pull between them. It's what gives us weight on Earth, and it governs everything from the motion of satellites in space to the behavior of black holes. Next, we have electromagnetism, which is responsible for a wide range of phenomena we encounter every day. Electromagnetic forces govern how charged particles interact. It's the force behind electricity and magnetism, which are intimately connected. In fact, when an electric current flows through a wire, it generates a magnetic field around it. Similarly, moving magnets can induce an electric current. Electromagnetism is the force that governs the behavior of atoms and molecules, and it's what keeps electrons bound to the nucleus of an atom. Without electromagnetism, the universe would be a very different place. Atoms wouldn't hold together, and the structure of matter itself would fall apart. The electromagnetic force is much stronger than gravity, but it has a much shorter range. It is, however, incredibly important for the functioning of everyday life. The third force is the strong nuclear force, which is responsible for binding the nuclei of atoms together. It is the strongest of the four forces, but it only acts at the incredibly small scale of atomic nuclei. The strong force binds protons and neutrons in the nucleus, overcoming the repulsive electromagnetic force that tries to push the positively charged protons apart. Without this force, atoms wouldn't be stable, and the elements we know and depend on wouldn't exist. It's also responsible for the energy released in nuclear reactions, like the ones in the Sun and nuclear power plants. Lastly, we have the weak nuclear force, which plays a crucial role in the process of radioactive decay. The weak force is responsible for the transformation of one type of particle into another, and it's involved in processes like beta decay, where a neutron turns into a proton, emitting an electron and an antineutrino in the process. The weak force is vital in processes that drive the energy production in stars, and also helps regulate the fundamental behavior of matter at the subatomic level. Though weaker than the strong nuclear force and electromagnetism, the weak nuclear force has a critical role in shaping the universe as we know it. Together, these four forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, form the bedrock of modern physics. They explain nearly all the phenomena we observe, from the motion of planets in distant galaxies to the behaviour of tiny particles inside atoms. The standard model of particle physics, which is the framework scientists use to understand the interactions between particles, is built around these four forces. But as comprehensive as this model is, it's not complete. There are still mysteries left unsolved, and scientists have long suspected that there may be other forces hidden from our current understanding waiting to be discovered. It's this very question, the search for forces beyond the familiar four, that brings us to the topic of a potential fifth force. The anomalies observed in experiments like Muon G2 and at CERN's LHCb experiment have sparked a new wave of interest in the possibility of forces that operate beyond the standard model. The idea that there might be more forces that we've yet to uncover, challenges everything we thought we knew. And it raises the tantalizing possibility that the universe is even more intricate and mysterious than we could ever imagine. As we continue to explore the possibilities of a fifth force, we'll need to examine these anomalies more closely, understanding how they point us toward new realms of physics. But first, it's important to appreciate how far we've come in our understanding of the forces that govern our universe, and how these discoveries set the stage for the mysteries we're about to unravel. So, what if there is a fifth force? What would it mean for our understanding of the universe? What could it reveal about the hidden dimensions of reality? The search for a fifth force is a journey into the unknown, one that could redefine the very nature of space, time, and the forces that shape our existence. Let's take the next step in this exploration, looking at how the Muon G2 experiment challenged our assumptions about the forces of nature. To truly understand the nature of forces, it's essential to grasp the concept of what makes a force fundamental. After all, the forces that shape the universe around us, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are not just random interactions. These are the core building blocks that govern everything from the smallest particles to the largest cosmic structures. They are fundamental because they represent the most basic, unbreakable, and irreducible aspects of nature. But what exactly does that mean? What sets them apart from other forces that might seem like forces but aren't considered fundamental? At its most basic level, a fundamental force is one that cannot be reduced to anything simpler. It's a force that doesn't arise from a combination of other forces or interactions. When we observe the four known forces, gravity, electromagnetism, the strong force, and the weak force, we see that they are not just arbitrary phenomena. Each of them serves a distinct essential function within the framework of the universe. They shape the interactions between particles, dictate the behaviour of matter, and determine how the universe evolves from moment to moment. These forces govern everything from how atoms stay together to how stars burn their fuel, and even the very shape of space-time itself. One way to think about why these forces are considered fundamental is to consider what they do and how they work. Fundamental forces operate at the most basic level of the universe. For example, gravity is responsible for the attraction between objects with mass. It determines how planets orbit stars, how objects fall to Earth, and how galaxies hold together. Gravity operates over vast distances, and although it is the weakest of the four forces, it governs the large-scale structure of the universe. Electromagnetism, on the other hand, deals with the interactions between electrically charged particles. It's the force behind everything from lightning to the way atoms bond together to form molecules. The electromagnetic force is responsible for the interactions between electrons and protons, which hold atoms together. It's also the reason for the phenomena we observe with magnets, electric currents, and electromagnetic radiation, such as light. Electromagnetism is incredibly strong compared to gravity, but its effects only extend to objects with charge. Unlike gravity, which operates between all objects with mass, electromagnetism works only between particles that have electric charge. Then, there's the strong nuclear force. This is the force that holds the nuclei of atoms together. It binds protons and neutrons inside the nucleus of an atom, overcoming the repulsive force of the positive charges between protons. This force is extremely powerful, but it only acts over very short distances, on the scale of atomic nuclei. Without the strong nuclear force, the universe would be a very different place. Atoms would not be stable, and the elements we depend on would not exist. In essence, the strong force is what makes matter stable, and gives rise to the structure of the universe at the microscopic scale. The weak nuclear force, though less well known, is just as essential. It governs processes like radioactive decay, in which unstable nuclei transform into more stable ones. The weak force is also responsible for the reactions that fuel the sun. Without it, stars wouldn't be able to shine, and life as we know it wouldn't exist. The weak force is the mediator of processes that change the fundamental properties of particles, such as the transformation of neutrons into protons. It operates at a very short range and is weaker than both the strong force and electromagnetism, but it is crucial for the processes that power the universe. So why are these forces considered fundamental? The answer lies in the fact that no other forces can be reduced to them. They don't emerge from other forces, nor can they be explained by a more fundamental force. Instead, these forces form the very fabric of reality. They are the rules of the game, setting the parameters for all interactions in the universe, from the tiniest subatomic particle to the largest galaxies. But here's where it gets interesting. As fundamental as these four forces seem, scientists have long suspected that they may not be the whole story. In fact, physicists have been searching for a fifth force for quite some time. The idea is that there could be additional, previously undiscovered forces that govern the interactions of particles in ways we don't yet understand. These hidden forces could be operating in parallel with the four known forces, influencing the behavior of particles in subtle ways, just as we're seeing with the anomalies observed in the Muon G2 experiment and the LHCb experiment at CERN. The search for a fifth force is rooted in the limitations of the standard model of particle physics, which describes the four fundamental forces we know. While the standard model has been incredibly successful in explaining a wide range of phenomena, there are still gaps in our understanding. For example, the standard model doesn't incorporate gravity. It doesn't explain dark matter, which makes up most of the mass in the universe. It doesn't fully account for the mysterious properties of dark energy, which is thought to drive the accelerated expansion of the universe. And most importantly, the standard model leaves us with an incomplete picture of the interactions between fundamental forces at the most basic level. The idea of a fifth force is an intriguing one, but it also raises important questions. What would this force look like? What would it interact with? Could it be the key to unlocking the mysteries of dark matter and dark energy? Could it provide insight into the nature of space and time itself? These are the questions that have driven scientists to explore the possibility of a fifth force, and it's precisely what makes the anomalies we're seeing in experiments like Muon G2 and LHCb so fascinating. In some ways, the search for a fifth force is not just about discovering something new, it's also about refining our understanding of the forces we already know. When we talk about a fifth force, we're not simply imagining something outside the realm of our current understanding. Instead, we're trying to reconcile the forces we've already discovered with the gaps in our knowledge. If there is indeed a fifth force, it may very well reshape our understanding of the universe, offering new insights into the very fabric of reality. To explore this idea further, we need to look more closely at the experiments that have raised the possibility of a fifth force. What are these anomalies, and how do they point to something beyond the known forces? The answers may be more profound than we can even imagine, but before we dive into these groundbreaking experiments, it's essential to understand the framework that defines our current view of the universe, one based on four fundamental forces, and in doing so, we'll be better equipped to explore the possibilities that lie ahead. Throughout history, the discovery of new forces has reshaped our understanding of the universe. The four fundamental forces we know today, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, have been essential in explaining the behavior of matter and energy. But as science has advanced, so has the realization that these forces might not be the entire story. As early as the 19th century, physicists began to wonder whether there were other forces yet to be discovered, forces that could potentially unlock new realms of physics and explain phenomena that were previously mysterious. The search for these forces, often referred to as the hunt for new forces, has been a central part of the development of modern physics. The earliest force we identified, gravity, was recognized long before the advent of modern science. Its effects were observed by ancient civilizations, but it wasn't until Isaac Newton in the 17th century that we gained a deeper understanding of gravity. Newton's law of universal gravitation described gravity as a force that attracts objects with mass toward each other. Newton's groundbreaking work set the stage for understanding how celestial bodies interacted, explaining everything from the falling apple to the orbits of planets. But even in the wake of such a monumental discovery, the quest to understand forces continued. As scientists peered deeper into the workings of the universe, they began to question whether there might be forces beyond gravity that we were unaware of. In the 19th century, the discovery of electromagnetism began to challenge the notion that gravity was the only force at work in the universe. The unification of electricity and magnetism into a single force, electromagnetism, by scientists like James Clerk Maxwell, demonstrated that the world of the very small, the realm of atoms and subatomic particles, behaved differently from the cosmic scale of Newtonian physics. Electromagnetism could explain the behavior of light, electricity and magnetism, and it became a force that governs a wide range of phenomena, from the behavior of atoms to the operation of electrical devices. Then came the discovery of the strong and weak nuclear forces in the 20th century. The strong force, responsible for binding protons and neutrons together in the nucleus of an atom, was essential for understanding how matter itself was structured. Without the strong nuclear force, atoms couldn't exist as we know them. The weak force, on the other hand, was essential for understanding processes like radioactive decay and nuclear reactions that power the stars. These forces, while operating on a subatomic scale, were critical for understanding the interactions between particles and how the universe behaves on the smallest scales. Yet even with the identification of these forces, one question remained. Are there more forces waiting to be discovered? Could there be additional forces hidden in the shadows, forces that we have yet to detect but that play a role in shaping the universe? The search for new forces has been a tantalizing possibility in the world of theoretical physics, and it has led to the formulation of many theories that extend beyond the standard model of particle physics. The standard model, which has been incredibly successful in explaining the behavior of elementary particles, incorporates the electromagnetic, weak and strong forces, but leaves out gravity. It also doesn't account for certain mysterious phenomena, such as dark matter and dark energy. These gaps in our understanding have driven scientists to consider the possibility of new forces that might help explain the parts of the universe that remain unexplained. One of the first major hints of a potential new force came in the 20th century, with the discovery of anomalies in the behavior of particles that didn't quite fit with the predictions of the standard model. In the 1970s, scientists began to notice strange behaviors in the interactions of particles, particularly in experiments involving the weak force. These anomalies sparked the idea that there might be a new force at work, one that was yet to be identified and understood. The search for new forces has continued into the 21st century, with the advent of advanced particle accelerators and experiments that push the boundaries of our knowledge. One of the most well-known places where these searches take place is the Large Hadron Collider, LHC, at CERN. which has provided us with some of the most exciting results in recent physics. The discovery of the Higgs boson in 2012, for example, was a monumental achievement that confirmed the existence of the Higgs field, a fundamental aspect of the Standard Model. But even with this success, the hunt for new forces continues. In fact, it's in experiments like those at the LHC that we've seen some of the most intriguing anomalies that suggest the possibility of forces beyond the known four. In particular, experiments such as the Muon G2 and LHCb at CERN have revealed deviations from the predictions of the Standard Model, anomalies that hint at the presence of new forces or interactions. These anomalies are subtle and require careful examination, but they represent some of the most exciting potential breakthroughs in modern physics. The Muon G2 experiment, for instance, revealed that the magnetic moment of the muon, a property that tells us about how the muon interacts with magnetic fields, was slightly different from what the Standard Model predicts. This discrepancy has led some scientists to propose the existence of a new force that could be influencing the muon's behaviour. Similarly, the LHCb experiment has observed unexpected patterns in the behaviour of B mesons, another type of subatomic particle. These particles, which are involved in weak force interactions, seem to behave in ways that contradicted the Standard Model's predictions. This has sparked renewed interest in the possibility of a new force, one that could explain these deviations and provide insight into the mysteries of the universe. But why are these anomalies so significant? The answer lies in the fact that the Standard Model is, for the most part, a remarkably successful theory. It has explained a wide range of phenomena and has stood the test of time. However, it's not perfect. There are still questions it can't answer. It doesn't explain the nature of gravity at the quantum level, for example. It doesn't provide an explanation for dark matter, which makes up a significant portion of the universe's mass. And it doesn't account for the accelerated expansion of the universe, which is attributed to dark energy. These gaps in our knowledge are what motivate physicists to look for new forces that might help fill in the blanks. The potential discovery of a fifth force would not just be a new addition to the list of forces we already know, it would be a game changer. It could reshape our understanding of the fundamental laws of nature and provide answers to some of the most profound questions in science. Could this new force be the key to understanding dark matter and dark energy? Could it be the missing link that unites the forces of nature into a single, unified theory? These are the questions that drive the search for new forces, and they are questions that could lead to some of the most profound discoveries of our time. As we look ahead, the quest to discover new forces is far from over. With experiments like Muon G2 and LHCb pushing the boundaries of our understanding, we are on the cusp of what could be a revolutionary breakthrough in physics. But before we can fully comprehend what these anomalies mean, we must first explore the details of the experiments themselves. What are the results from these experiments, and how do they point us toward the possibility of a fifth force? That's where the story begins to get even more fascinating. The Muon G2 experiment has become one of the most discussed and anticipated experiments in modern physics. At first glance, the idea of studying a single particle, the muon, might seem too narrow to uncover anything groundbreaking. After all, muons are relatively short-lived and have a mass roughly 200 times greater than that of an electron. They're not even stable, decaying into other particles within a fraction of a second after being produced. So, why is this experiment so important? What can the behaviour of this short-lived exotic particle tell us about the fundamental forces of nature? To understand why the Muon G2 experiment is so significant, we must first consider the unique properties of the muon itself. The muon is part of a family of particles known as leptons, which also includes electrons and neutrinos. Like the electron, the muon carries a negative electric charge, and it interacts with other particles through the electromagnetic force. However, the muon is much heavier than the electron, which makes it behave differently when placed in a magnetic field. One of the key properties of particles like the electron and the muon is their magnetic moment. The magnetic moment tells us about how a particle interacts with magnetic fields. In simple terms, it is a measure of how strongly a particle behaves like a tiny magnet. The magnetic moment of the muon, much like that of the electron, is governed by the electromagnetic force. However, due to the muon's larger mass, its behavior in a magnetic field is more pronounced and can reveal subtle differences that are extremely sensitive to the nature of the forces acting on it. In the 1940s, scientists first began to investigate the magnetic moment of the electron, and later the muon. These investigations helped scientists test and refine the predictions of quantum electrodynamics, QED, the theory that describes how light and matter interact. QED is one of the most successful theories in the history of science, providing highly accurate predictions that have been confirmed by countless experiments. However, the predictions of QED were based on the assumption that the electromagnetic force is the only force acting on particles like the muon. As researchers continued to study the muon, they found that its magnetic moment deviated slightly from the predictions made by QED. In other words, something else seemed to be affecting the muon's behavior in ways that were not accounted for by the standard model. This led to the hypothesis that there could be additional forces at play, forces that were not part of the four known fundamental forces: gravity, electromagnetism, the strong force, and the weak force. Enter the Muon G2 experiment, an ambitious project designed to measure the muon's magnetic moment with unprecedented precision. The experiment takes place at Fermilab, a particle physics laboratory located near Chicago, and is a continuation of earlier work that began in the 1970s. The goal of the experiment is to measure how the muon interacts with a magnetic field in a way that can detect any potential deviations from the predictions of the standard model. The Muon G2 experiment uses a unique approach to measure the muon's magnetic moment. Muons are produced in a particle accelerator and then injected into a storage ring, a circular track where the muons are kept circulating for several milliseconds. As the muons travel around the ring, they pass through a magnetic field that causes them to wobble or precess, in a manner similar to a spinning top. The degree to which the muons precess depends on their magnetic moment. By measuring this precession very precisely, scientists can determine the muon's magnetic moment and compare it to the theoretical predictions. Now, the twist in all of this comes from the fact that, in addition to the known forces, there are other quantum effects that can influence the muon's magnetic moment. For example, the presence of virtual particles, particles that momentarily pop into existence and then vanish, can contribute to the muon's behavior in a magnetic field. These virtual particles are part of the quantum vacuum, and while they don't directly interact with the muon, they can still affect its magnetic moment through a phenomenon called the anomalous magnetic moment. When the Muon G2 experiment was set up, scientists had a very clear expectation of what the result would be. Based on the standard model, they predicted that the muon's magnetic moment would align with the previously measured value. However, when the results started to come in, the scientists found something unexpected. The measured value of the muon's magnetic moment was slightly larger than predicted by the standard model. This discrepancy, though small, was highly significant. It suggested that something was causing the muon to behave in ways that the current understanding of physics couldn't explain. The difference between the experimental result and the standard model prediction was small, but it was statistically significant. In fact, the discrepancy was large enough to suggest the presence of a new force or interaction beyond what was known. Scientists immediately began to consider the possibility that the extra force was related to the unknown interactions between particles. Could this anomaly be evidence of a fifth force, one that interacts with the muon but has never been observed in other experiments? To make sense of the results, researchers began to explore theories that could explain the deviation in the muon's magnetic moment. One of the leading theories was that the muon might be interacting with a new, previously undetected particle. Some researchers suggested that this particle could be a type of force carrier, like the photon for electromagnetism, or the W and Z bosons for the weak force. If such a particle existed, it could mediate a new force, one that affects the muon in a way that the standard model doesn't account for. The possibility of a new force emerging from the Muon G2 experiment sparked renewed interest in the hunt for new physics. Scientists began to wonder whether this anomaly could be the first hint of a deeper, more fundamental change in our understanding of the universe. Could this anomaly be evidence of a new interaction, perhaps related to dark matter or dark energy? Could it be a sign that the forces we currently understand are just the beginning of something much more complex? The results of the Muon G2 experiment, along with similar anomalies observed at CERN's LHCb experiment, suggest that we may be on the brink of a new era in physics. The discovery of a fifth force, one that interacts with the muon and potentially other particles, would be a groundbreaking development, one that could lead to a fundamental rewrite of the laws of nature. While the results of the Muon G2 experiment are still under careful scrutiny, they represent a significant step forward in our understanding of the universe. They challenge us to think beyond the familiar forces and to consider the possibility that there is much more to discover. As we move forward in this exploration, we'll look at how the LHCb experiment has provided additional evidence that may support the idea of a fifth force, and how these anomalies fit into the larger puzzle of understanding the fundamental nature of reality. The story is far from over, and the Muon G2 experiment has opened up a new chapter in our quest to understand the universe. What's next? Only time and more data will tell. The LHCb experiment at CERN has provided some of the most fascinating and perplexing results in recent years. While much of the world's attention is focused on the discovery of the Higgs boson and the implications it has for our understanding of the universe, another set of experiments at the Large Hadron Collider LHC has raised some questions that challenge the very foundation of particle physics. These questions stem from an unexpected behaviour observed in a class of particles known as B mesons. The anomalies in the data from the LHCb experiment are at first glance subtle, but they have the potential to unlock new insights into the forces that govern the universe. To understand why the LHCb experiment is so important, we need to dive into the world of B mesons. B mesons are particles made up of a bottom quark and either an up or a down quark. These particles are unstable and decay rapidly, but they have a particular significance in particle physics because they allow scientists to study the weak nuclear force, one of the four known fundamental forces. The weak force is responsible for processes like radioactive decay, and it plays a key role in how subatomic particles interact with one another. It's the force that causes one type of quark to transform into another, changing the properties of the particle and producing a variety of other particles in the process. The LHCb experiment, one of the experiments conducted at CERN's Large Hadron Collider, was designed to study the interactions of B mesons and other particles that involve the weak force. This experiment has provided crucial data on how particles decay and how they behave in extreme conditions, such as high-energy environments. The goal of the experiment was to study the fundamental properties of the weak force and test the predictions made by the standard model of particle physics. However, as the data started to come in, researchers began to notice something odd. In certain interactions involving B mesons, the experiment revealed anomalies, deviations from the expected results according to the standard model. Specifically, the observed decay rates of B mesons did not match the predictions of the standard model. This raised an eyebrow among physicists. The discrepancies were subtle, but they were statistically significant enough to suggest that something was wrong with the current understanding of particle interactions. These anomalies came in the form of flavour-changing neutral currents, a process in which a quark changes flavour without emitting a charged particle. The standard model predicted that this should happen very rarely, but the LHCb data suggested it was happening more often than expected. Moreover, these interactions seem to be violating the so-called lepton flavour universality principle, which states that all leptons, such as electrons, muons and tau particles, should interact in the same way when subjected to the same forces. The data from the LHCb experiment, however, suggested that muons and electrons were not behaving identically in certain particle decays, which could indicate that something was influencing the muons in a way that did not affect electrons. This discrepancy raised an important question. Could these anomalies point to the existence of a new force, one that interacts differently with different types of particles? Could there be an interaction that the standard model does not account for, one that could help explain these unexpected results? The possibility of a fifth force started to gain traction, and the LHCb anomalies became a key part of the conversation. The idea that these anomalies might be linked to a fifth force is supported by the fact that the discrepancies observed in the LHCb data are consistent with some of the results seen in the Muon G2 experiment. In both cases, the anomalies involve the behaviour of leptons, particles like electrons and muons, and in both cases the results suggest that something beyond the standard model is at play. These two experiments, though focused on different particles and different interactions, appear to be telling a similar story. The possibility that there is an undiscovered force influencing the way particles behave. One theory that has been proposed to explain these anomalies is that a new force could be interacting with B mesons and muons in a way that doesn't affect electrons or other particles in the same manner. This new force might be a very weak interaction, which is why it hasn't been detected before, but strong enough to influence the behaviour of certain particles. Some scientists believe that this new force could be related to dark matter, the mysterious substance that makes up most of the mass in the universe but has yet to be directly detected. Dark matter interacts very weakly with regular matter, which could explain why it has remained elusive. If the anomalies observed in the LHCb experiment are due to the influence of dark matter or another unknown force, it would be a major breakthrough in our understanding of the universe. Other theories propose that the anomalies could be due to the existence of a new type of particle, one that mediates this fifth force. In this scenario, the new particle would be a force carrier, similar to how the photon is the force carrier for electromagnetism, or the gluon for the strong nuclear force. This new particle could interact with B mesons and muons in a way that doesn't affect other particles, explaining the observed deviations from the standard model. While this is still speculative, it's an exciting possibility that could provide a path forward in the search for a fifth force. The LHCb anomalies are not just small deviations in data, they represent a challenge to the existing framework of particle physics. The standard model has been incredibly successful in explaining a wide range of phenomena, but these anomalies suggest that it may not be the complete picture. If the results of the LHCb experiment are confirmed, they could indicate the presence of a new force or particle that has been hidden in plain sight, waiting to be discovered. The implications of such a discovery would be profound, potentially reshaping our understanding of the fundamental forces of nature and providing new insights into the mysteries of dark matter, dark energy, and the very fabric of the universe. As we continue to investigate these anomalies, it's important to remember that science is not a static field. Our understanding of the universe is constantly evolving, and new discoveries often challenge our most cherished ideas. The LHCb anomalies are just one piece of the puzzle, but they represent a promising lead in the search for new physics. Whether these deviations are the result of a fifth force, a new particle, or some other unknown interaction, they provide an exciting glimpse into the future of particle physics. And as we continue to gather more data and refine our experiments, we may be on the verge of a discovery that could change everything. As we look ahead to the future, it's clear that the search for new forces is far from over. The Muon G2 experiment and the LHCb experiment at CERN have already provided us with tantalizing hints, and scientists around the world are working tirelessly to uncover the truth. But for now, the anomalies remain a mystery, one that may hold the key to unlocking the next great breakthrough in our understanding of the universe. The term dark dimension may sound like something straight out of a science fiction novel, a mysterious and unexplored realm where the normal rules of physics no longer apply. However, when scientists use this phrase, they're not invoking fantasy or speculation, but discussing some of the most profound and challenging aspects of modern physics. The concept of a dark dimension typically refers to the possibility that there could be additional, hidden dimensions of space beyond the familiar 3 dimensions of space and one of time that we experience in everyday life. These extra dimensions, if they exist, could potentially help explain some of the deepest mysteries of the universe, including the anomalies observed in experiments like Muon G2 and LHCb. To understand what a dark dimension might mean, it's helpful to start with the idea that our universe may not be as straightforward as it seems. For centuries, humans have believed that we live in a universe defined by the 3 dimensions of space, length, width, and height, and 1 dimension of time. These dimensions are the framework through which we perceive reality. But this classical view began to shift in the early 20th century with the advent of Albert Einstein's theory of relativity, which fundamentally changed our understanding of space and time. Einstein's work showed that space and time are not separate entities but are intertwined into a single 4-dimensional fabric known as space-time. This idea has been confirmed by a wide range of experimental evidence, including the bending of light around massive objects, as predicted by general relativity. However, relativity also led to the realization that space-time might not be the full picture. Theories such as string theory, which is currently one of the most promising frameworks for understanding the fundamental forces of nature, propose that the universe could have more than just the 4 dimensions we're familiar with. According to string theory, the universe could contain additional dimensions, perhaps as many as 10 or even 11, that are compactified or curled up and thus hidden from our perception. These extra dimensions are not the kind of space we're used to, where we can move freely in every direction. Instead, they might be so small and tightly curled that they are imperceptible to us at everyday scales. But what does this have to do with the concept of a dark dimension? A dark dimension in this context refers to the possibility that there could be dimensions that we can't directly observe, either because they are hidden on very small scales or because they interact with our familiar dimensions in ways that are difficult to detect. In certain theoretical models, these hidden dimensions could be the key to explaining phenomena that the standard model of particle physics cannot. For example, they might provide a mechanism for dark matter, a mysterious substance that makes up a significant portion of the universe's mass, but doesn't emit or interact with electromagnetic radiation in a way that we can detect. If these hidden dimensions exist, they could provide the framework through which dark matter interacts with ordinary matter. The idea of dark dimensions also ties into the possibility of a 5th force, one that could be mediated by new particles or interactions that arise from these extra dimensions. In certain models, the force could be tied to the curvature or behavior of space within these hidden dimensions. For example, some theories suggest that the 5th force might be a manifestation of gravitational effects that are linked to these extra dimensions. If a new force is indeed at play in the Muon G2 and LHCb anomalies, it could be connected to the hidden structures of space and time that we have yet to fully comprehend. Moreover, dark dimensions could also be responsible for other phenomena that have puzzled physicists, such as the nature of dark energy. Dark energy is the term used to describe the mysterious force that seems to be driving the accelerated expansion of the universe. It makes up around 68% of the universe's total energy density, yet it remains completely undetectable by current means. Some theories suggest that dark energy could be related to the energy of these hidden dimensions, acting as a kind of force that affects the expansion of the universe on the larger scales. Another potential connection between dark dimensions and the anomalies observed in particle physics experiments is the idea of supersymmetry, a theory that proposes that every particle we know has a partner particle that differs in its properties. Supersymmetry also suggests that the universe might contain additional hidden symmetries that could be related to these dark dimensions. If supersymmetry holds true, then there could be new particles in these hidden dimensions that could explain some of the strange behaviors observed in experiments like Muon G2 and LHCb. But while these theories are compelling, it's important to note that they remain speculative. The concept of dark dimensions, though supported by some leading theories in physics, is still a subject of active research and debate. The extra dimensions proposed by string theory, for example, have not yet been observed directly. Similarly, the fifth force suggested by the anomalies in the Muon G2 and LHCb experiments has not been conclusively proven. The idea of dark dimensions and new forces is still very much in the realm of theoretical physics, and much work remains to be done to determine whether these ideas reflect the true structure of the universe. Despite the uncertainty, the very possibility that there might be hidden dimensions influencing the fundamental forces of nature has profound implications for our understanding of reality. If the anomalies observed in these experiments are indeed caused by interactions with hidden dimensions, it would represent a revolutionary shift in our understanding of physics. It would mean that there is more to the universe than meets the eye, and that the foreknown forces are only part of a much more complex and interconnected system of interactions. The search for dark dimensions, and the forces that might be hidden within them, is one of the most exciting frontiers in modern physics. It's a search that could answer some of the most pressing questions about the universe, questions about the nature of dark matter, dark energy, and the very structure of space and time itself. It's a search that may ultimately lead to a deeper understanding of the forces that govern the universe, revealing new connections between the known and the unknown, between the observable and the hidden. As we continue to explore the possibility of dark dimensions and new forces, we must remember that the path ahead is uncertain. Theories may evolve, and new discoveries may come from unexpected places. But one thing is certain: the search for a deeper understanding of the universe, one that includes these hidden dimensions and forces, is a journey that will shape the future of physics for years to come. And as we continue to investigate these phenomena, we may find ourselves on the brink of a discovery that could change everything we thought we knew about the universe. To truly grasp the significance of the anomalies in the Muon G2 and LHCb experiments, we must first understand the particles at the heart of these discoveries, the muon and the B meson. These particles are far from ordinary, and their behavior challenges our understanding of the fundamental forces in ways that ripple through the entire framework of modern physics. Muons and B mesons have provided us with some of the most surprising data, and their strange interactions have pushed scientists to reconsider the very laws that govern the universe. But what makes these particles so special, and how have they changed the course of physics? The muon is part of the lepton family, which includes electrons and neutrinos. However, the muon is different from the electron in a significant way. It's much heavier. While an electron has a mass of about 9.11 times 10 to the power of minus 31 kilograms, a muon is roughly 200 times more massive, making it a heavy cousin in the family of leptons. Despite this difference in mass, muons and electrons share many similar properties. Both carry a negative charge and interact with other particles via the electromagnetic force. However, what makes the muon particularly interesting is its behavior in a magnetic field, a key feature that has led to the Muon G2 experiment. In the 1940s, scientists began to study the muon's magnetic moment, which refers to the way the muon interacts with magnetic fields. The magnetic moment of the muon is not just a property of the particle, but a key piece of the puzzle in understanding how the muon interacts with the world around it. According to the standard model, the muon's magnetic moment should behave in a specific way when subjected to a magnetic field. The standard model provides precise predictions for how particles like the muon should behave, based on the forces and interactions that we already understand. However, when the Muon G2 experiment was set up, researchers began to notice something strange. The muon's magnetic moment didn't behave exactly as the standard model predicted. Instead, the experimental results showed a discrepancy. The muon's magnetic moment was slightly larger than expected. This tiny difference, though small, was highly significant because it suggested that the muon was interacting with something beyond the known forces of nature. Could this anomaly point to a new force, one that is not part of the standard model? As the results of the Muon G2 experiment were analysed, the idea that the muon might be interacting with an unknown force gained traction. The anomaly could be due to the influence of a new particle, one that interacts with the muon in ways that have not been observed before. This new force would not only explain the discrepancy in the muon's magnetic moment, but also represent a breakthrough in our understanding of particle interactions. The possibility that the muon's behaviour was influenced by a fifth force, one that is undetectable through traditional methods, has profound implications for our understanding of the universe. At the same time, another set of experiments at CERN's Large Hadron Collider was revealing similar anomalies, this time involving B-mesons. B-mesons are composite particles made up of a bottom quark and another quark, such as an up or down quark. These particles play a key role in the study of the weak nuclear force, one of the four fundamental forces in nature. The weak force is responsible for processes like beta decay, in which a neutron transforms into a proton, releasing an electron and an antineutrino. But while the weak force is well understood, the behaviour of B-mesons in high-energy environments is not as straightforward. In particular, experiments at CERN's LHCb experiment have shown that B-mesons exhibit strange behaviours that don't quite fit with the predictions made by the standard model. For example, researchers noticed that certain decays of B-mesons appear to violate a principle known as lepton flavor universality. This principle asserts that all leptons, electrons, muons and tau particles should interact with the weak force in the same way. However, the LHCb data showed that muons and electrons were interacting differently in certain particle decays, suggesting that there might be an unknown force at play that affects the muons in ways it does not affect electrons. The discrepancies observed in the B-meson decays were subtle but significant. Just as with the muon anomaly, the LHCb results suggested that the weak force, as we currently understand it, might not be the full picture. There seemed to be an additional interaction influencing the B-mesons, one that was not accounted for by the standard model. This led scientists to consider the possibility that the B-mesons were experiencing a force, or interaction, that had been overlooked until now. Was this an indication of a new fifth force, similar to the one suggested by the Muon G2 experiment? The similarities between the two sets of anomalies, those involving the muon and those involving the B-mesons, are striking. In both cases, the results suggest that particles are behaving in ways that don't fit with the predictions of the standard model. In both cases, the data hints at the presence of an interaction or force that has been hidden from our current understanding. These findings have generated excitement and curiosity among physicists, as they point to the possibility that there is more to the universe than we've yet discovered. What makes these anomalies even more intriguing is the fact that they appear to be connected. If the muon's anomalous magnetic moment and the strange behaviour of B-mesons are both the result of the same underlying force, it would suggest that this force is not limited to one type of particle. It could be a universal force, one that affects a variety of particles in ways that we have not yet fully understood. This would be a profound discovery, as it would represent a major extension of the standard model, perhaps even hinting at a grand unification of the fundamental forces. So how have muons and B-mesons changed everything? They have provided us with a tantalizing glimpse of what could be a new force, one that operates in ways we have not yet imagined. The anomalies in both experiments suggest that there is still much to learn about the forces that govern the universe. These findings challenge the existing framework of particle physics, pushing us to reconsider our assumptions and explore new possibilities. As scientists continue to investigate these anomalies, the implications for the future of physics are enormous. The discovery of a new force would revolutionize our understanding of the universe and open up new frontiers of scientific inquiry. The search for new forces is far from over, and as we continue to explore the behavior of particles like the muon and the B-meson, we may find ourselves on the cusp of a discovery that will change the course of science. Whether the anomalies observed in these experiments ultimately point to a fifth force or some other unknown interaction, they have already changed the way we think about the fundamental laws of nature, and in doing so they have opened the door to a new era of physics, one where the mysteries of the universe are just waiting to be uncovered. The search for a fifth force, one that exists beyond the well-established four of gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, has been a tantalizing prospect in modern physics for decades. The possibility that there might be a hidden force at work in the universe challenges everything we know about the structure of nature and the laws that govern it. While the anomalies observed in the Muon G2 and LHCb experiments have sparked new interest in the idea of a fifth force, these anomalies are not the first time that scientists have speculated about the existence of additional forces. In fact, various theories of the fifth force have been proposed over the years, each with its own potential explanations and implications. But what might this fifth force look like? Could it be linked to dark matter or dark energy? Or is it a completely new interaction that we have yet to comprehend? Before diving into the specific theories, it's worth revisiting the fundamental forces that govern the behavior of particles in the Standard Model. As we know, the Standard Model includes four forces: gravity, electromagnetism, the strong force, and the weak force. These forces explain a wide range of phenomena, from the motion of planets and stars to the interactions between quarks and leptons. Yet, despite the success of the Standard Model, there are still unanswered questions. Gravity, for example, is not incorporated into the Standard Model, and the theory of quantum gravity, which would unite gravity with the other forces, remains elusive. Additionally, the existence of dark matter and dark energy, which together make up the majority of the universe's mass and energy, cannot be explained by the Standard Model. These gaps have driven scientists to consider the possibility that there might be a fifth force, an unknown interaction that could provide answers to some of the most fundamental questions in physics. Several theories have emerged over the years, each offering a potential explanation for what this fifth force could be and how it might work. One of the leading theories of the fifth force comes from the idea of dark matter. Dark matter is a mysterious substance that does not interact with electromagnetic radiation, which is why it is invisible to telescopes and other traditional observational tools. It has been detected indirectly through its gravitational effects, which can be seen in the motion of galaxies and galaxy clusters. While dark matter is thought to make up around 27% of the mass of the universe, its exact nature remains one of the biggest puzzles in physics. Some theories propose that dark matter could be the mediator of a fifth force. In these models, dark matter particles, often theorized to be weakly interacting massive particles, WIMPs, could interact with regular matter via a new force that is distinct from the known four. This fifth force could be responsible for the gravitational-like effects that we observe with dark matter, and its interaction with ordinary matter could explain the anomalies seen in experiments like Muon G2 and LHCb. This theory would also help explain the lack of detection of dark matter particles through traditional means, as their weak interactions with regular matter would make them difficult to observe. Another possibility is that the fifth force could be related to dark energy, the mysterious force that is driving the accelerated expansion of the universe. Dark energy is thought to make up about 68% of the total energy density of the universe, yet it remains completely undetectable except for its gravitational effects on the large-scale structure of the universe. Some theories suggest that dark energy could be the result of an additional force that interacts with space itself, influencing its expansion. If dark energy is indeed related to a fifth force, it could help explain the anomalies seen in particle physics experiments. The fifth force might interact with other particles in ways that are not accounted for by the Standard Model, offering a clue to the nature of dark energy and its role in the evolution of the universe. There are also theories that suggest the fifth force could be linked to extra dimensions. As we've discussed earlier, string theory and other higher dimensional models propose the existence of additional spatial dimensions beyond the familiar three. In these models, the forces of nature could be unified in higher dimensional space, and the fifth force might arise from interactions that take place in these hidden dimensions. In such scenarios, the fifth force could be mediated by new particles that interact with both the familiar four dimensions of space and time and the extra dimensions predicted by string theory. This type of force might not be detectable in our everyday experience because its effects would only be noticeable at very small scales, such as those explored in particle accelerators like the LHC. However, the anomalies observed in experiments like Muon G2 and LHCb might be a hint that we are detecting the first signs of such a force. One theory that has gained attention in recent years is the idea of a dark photon, a hypothetical particle that could mediate a fifth force related to dark matter. The dark photon is similar to the ordinary photon that mediates the electromagnetic force, but it would interact only with dark matter and certain particles, making it invisible to most detection methods. If dark photons exist, they could be the long-sought mediator of a new force that affects both visible and dark matter, offering an explanation for the anomalies observed in particle physics experiments. This theory has been suggested as a potential explanation for the discrepancies in the muon's magnetic moment and the unusual behavior of B mesons in the LHCb experiment. There are also more exotic ideas about the nature of the fifth force. One such theory involves modified gravity models, where the force of gravity itself is altered on small scales. These models suggest that the force of gravity might behave differently at microscopic distances, potentially explaining the anomalies seen in particle interactions. In these models, the gravitational force is not the same as we experience in everyday life, but could change in subtle ways at the subatomic level, influencing the behavior of particles like the muon and the B meson. This type of modified gravity would provide an alternative explanation for the discrepancies observed in experiments without requiring the introduction of a new fundamental force. As exciting as these theories are, it is important to recognize that none of them have been definitively proven. The evidence from experiments like Muon G2 and LHCb is still preliminary, and much more data will be needed to confirm whether these anomalies are indeed the result of a fifth force, or whether they point to some other unknown interaction. However, the possibility of a fifth force has inspired a great deal of theoretical work as scientists attempt to understand the implications of these anomalies and develop new models that could explain the results. The search for a fifth force is not just about discovering a new interaction, it is also about expanding our understanding of the fundamental nature of reality. The standard model of particle physics has been remarkably successful in explaining the behavior of particles and forces, but it is clear that there is still much to learn. The discovery of a fifth force would represent a profound shift in our understanding of the universe, providing insights into the nature of dark matter, dark energy, and the very structure of space-time itself. It would be a step toward a deeper understanding of the forces that govern the universe and the hidden dimensions of reality that remain beyond our reach. As we continue to explore the possibility of a fifth force, we must remain open to new ideas and theories that challenge our existing framework. The anomalies observed in the Muon G2 and LHCb experiments are just the beginning. With further research and experimentation, we may be on the cusp of one of the most exciting breakthroughs in modern physics, one that could unlock the secrets of the universe and change the way we think about space, time, and the forces that shape our reality. The standard model of particle physics is one of the most successful scientific theories ever developed. It describes the fundamental particles that make up the universe and the forces that govern their interactions, except for gravity. Over the course of the 20th century, this model has been refined through countless experiments, culminating in the discovery of key particles like the Higgs boson. The model has provided explanations for everything from the interactions between quarks and leptons to the forces that hold atoms together. It has allowed us to make incredibly precise predictions and has laid the groundwork for much of modern physics. Yet, despite its success, the standard model is incomplete. it cannot explain some of the most fundamental mysteries of the universe, such as the nature of gravity, dark matter, and dark energy. As such, it is increasingly clear that the Standard Model, while impressive, may not be the final word in our understanding of the universe. The Standard Model works by categorizing all known elementary particles into three groups: fermions, bosons, and the Higgs boson. Fermions include particles like quarks and leptons, which make up matter. Bosons are the force carriers, the particles that mediate the fundamental forces of nature. For example, the photon is the force carrier for electromagnetism. The W and Z bosons are responsible for the weak force, and the gluon mediates the strong force. The Higgs boson, discovered in 2012, is associated with the Higgs field, which gives particles their mass. The power of the Standard Model lies in its ability to describe how these particles interact. It provides a framework that explains how quarks combine to form protons and neutrons, how electrons orbit atomic nuclei, and how forces like electromagnetism and the strong force affect particles at the smallest scales. The model has been tested and confirmed in a wide variety of experiments, from the results of particle accelerators to the behavior of subatomic particles in everyday settings. The precision of these tests is remarkable, and the Standard Model has passed them all. However, there are several reasons why the Standard Model cannot be considered the ultimate theory of everything. One of the most glaring gaps is its inability to include gravity. Gravity, the force that governs the motion of planets and galaxies and holds us to the Earth, is the most familiar of all the forces. Yet it is not part of the Standard Model. The gravitational force is described by Einstein's theory of general relativity, which works exceptionally well on the large scale, explaining the motions of planets, stars, and galaxies. But when you start looking at the behavior of particles at the quantum level, general relativity breaks down, and gravity is no longer well understood. Another major gap in the Standard Model is its failure to account for dark matter and dark energy. Dark matter is a mysterious substance that makes up about 27% of the universe's mass, yet we cannot see it directly. Its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. Dark energy, meanwhile, is thought to account for about 68% of the universe's energy content, driving its accelerated expansion. Despite their enormous presence in the universe, neither dark matter nor dark energy fits into the framework of the Standard Model. We have no explanation for what they are or how they interact with the particles and forces described by the Standard Model. Additionally, the Standard Model cannot explain the hierarchy problem, which is the question of why the weak force is so much stronger than gravity, or why the masses of the fundamental particles differ so much from each other. There's also the issue of neutrino masses. While the Standard Model predicted that neutrinos should have no mass at all, we now know that they do, a discovery that came from observing neutrino oscillations, where neutrinos change from one type to another. This finding requires a modification to the Standard Model, but a satisfactory explanation remains elusive. These gaps in the Standard Model are why physicists have long suspected that there must be a deeper, more fundamental theory that can explain not only the forces and particles we already know, but also those that remain mysterious. The search for a theory of everything, one that can unify the Standard Model with general relativity, explain dark matter and dark energy, and provide a more complete understanding of the forces that govern the universe, has become one of the central goals of modern physics. In this context, the recent anomalies observed in the Muon G2 and LHCb experiments are incredibly significant. They suggest that there may be forces or particles that lie beyond the Standard Model, and that we may be on the brink of discovering something new and revolutionary. The possibility of a fifth force, one that interacts with muons, B-mesons, and potentially other particles in ways the Standard Model cannot explain, is one of the most exciting prospects in contemporary physics. If these anomalies are confirmed, they would point to the need for a new theory that extends or even supersedes the Standard Model. The idea of extending the Standard Model is not new. For decades, physicists have been working on theories like supersymmetry, which suggests that each particle in the Standard Model has a corresponding superpartner particle, and string theory, which proposes that all particles are actually vibrating strings of energy. These theories aim to explain the gaps in the Standard Model and unify the fundamental forces, including gravity, into a single framework. While these ideas are promising, they have not yet been experimentally confirmed, and they remain speculative. The anomalies observed in the Muon G2 and LHCb experiments provide a potential new pathway for exploring these deeper theories. For example, the idea of a fifth force could be tied to supersymmetry. In some versions of supersymmetry, new particles could exist that interact with known particles in ways not described by the Standard Model. These particles could help explain the anomalies observed in the Muon G2 experiment, where the muon's magnetic moment deviates from what the Standard Model predicts. In other versions of supersymmetry, the fifth force might be mediated by a new particle that interacts differently with different types of particles, such as muons or B mesons, leading to the strange behavior seen in the LHCb experiment. Similarly, the concept of dark matter could provide an explanation for the potential fifth force. If dark matter is composed of particles that interact via a new force, one that is not part of the Standard Model, then the anomalies observed in these experiments could be evidence of dark matter particles interacting with regular matter in ways we had not previously considered. The detection of such interactions could help solve the mystery of dark matter, which has remained undetected by traditional methods, despite making up a significant portion of the universe's mass. One of the most exciting aspects of the potential discovery of a fifth force is that it could lead to the unification of the four known forces in a way that the Standard Model cannot. Physicists have long sought a theory of everything, TOE, a single unified theory that explains all the forces of nature in one elegant framework. If the fifth force is real, it could be the key to unlocking such a theory, bringing us closer to understanding how gravity, electromagnetism, the strong force, and the weak force are connected, and perhaps even unifying them into a single force. The role of the Standard Model in all of this is crucial. While the model has been incredibly successful, it is clear that it is not the final answer. The anomalies observed in the Muon G2 and LHCb experiments, along with the mysteries of dark matter and dark energy, suggest that there is more to discover. The Standard Model has served as our best understanding of the fundamental particles and forces for nearly a century, but it is now being challenged by new data. Whether the fifth force proves to be real or not, the search for it is likely to lead to a deeper understanding of the universe, one that builds on the foundation of the Standard Model while extending it into new, uncharted territory. In the coming years, as experiments continue at places like CERN, we may find that the Standard Model needs to be expanded or replaced by a new framework that can explain the anomalies we are observing. The discovery of a fifth force could be the first step in this new chapter of physics, one that may ultimately reveal the true nature of the universe in ways we can't yet fully comprehend. Quantum mechanics has revolutionized our understanding of the microscopic world. It has provided a framework for explaining the behavior of particles at the smallest scales, where the familiar laws of classical physics no longer apply. This theory has been incredibly successful in predicting the behavior of atoms, subatomic particles, and the forces that govern their interactions. From the behavior of electrons in an atom to the phenomena of quantum entanglement, quantum mechanics has shown us a universe that is far stranger and more complex than we could have imagined. However, one of the most significant challenges in modern physics is how to reconcile quantum mechanics with general relativity, which describes the large-scale structure of the universe, including gravity. It's within this context that the search for a fifth force takes on new significance. Quantum mechanics, at its core, describes the probabilistic nature of particles and their interactions. In the quantum world, particles do not have definite positions or velocities until they are measured. Instead, They exist in a state of probability, described by a wave function, which encompasses all the possible states a particle could occupy. This inherent uncertainty and the ability for particles to exist in multiple states simultaneously are some of the most counterintuitive aspects of quantum mechanics. For example, in the famous double-slit experiment, particles like electrons and photons create an interference pattern, acting like both particles and waves at the same time. This strange behavior is a key feature of quantum mechanics. One of the most significant successes of quantum mechanics has been in describing the electromagnetic force. Quantum electrodynamics, QED, the quantum field theory that deals with electromagnetic interactions, has been incredibly successful in explaining the way photons, the force carriers of the electromagnetic force, interact with charged particles like electrons. QED has made predictions that match experimental results with incredible precision. In fact, the agreement between theory and experiment is so close that it has become a model of accuracy in theoretical physics. However, when it comes to the other forces, particularly gravity, quantum mechanics runs into trouble. While quantum mechanics is incredibly successful at describing the behavior of particles that interact via the electromagnetic, weak and strong forces, it cannot fully explain how gravity works at the quantum level. General relativity, Einstein's theory of gravity, describes gravity as the curvature of space-time caused by massive objects, but it does not fit with the principles of quantum mechanics. This has led to what is known as the problem of quantum gravity, the quest to develop a theory that can describe both the microscopic world of quantum mechanics and the macroscopic world of general relativity in a single unified framework. Now consider the idea of a fifth force. If such a force exists, it could potentially offer new insights into the relationship between quantum mechanics and gravity. The search for a fifth force is, in many ways, an attempt to understand how the known forces of nature fit together and to uncover any unknown interactions that may be lurking beneath the surface. Some of the anomalies observed in the Muon G2 and LHCb experiments suggest that there may be a new force that operates on a scale that quantum mechanics has not yet fully accounted for. Quantum mechanics, at its most basic level, operates through the exchange of force-carrying particles called bosons. In the case of the electromagnetic force, for example, the force carrier is the photon. Similarly, the strong and weak nuclear forces are mediated by gluons and W/Z bosons, respectively. But what if a new force, such as the fifth force, could be mediated by a new type of particle, one that operates differently from the known force carriers? This possibility has been suggested by some physicists who propose that such a particle could interact with existing particles in ways that quantum mechanics does not yet fully explain. One area where quantum mechanics and the idea of a fifth force intersect is in the study of quantum field theory, QFT, which is the framework that underpins the interactions between particles in quantum mechanics. In QFT, particles are seen as excitations or ripples in underlying quantum fields. These fields are responsible for the forces that particles experience. The electromagnetic field, for example, is the quantum field that gives rise to photons, which mediate the electromagnetic force. If a fifth force exists, it would likely be mediated by a new quantum field, one that interacts with particles in ways that we have not yet observed. The idea of a new quantum field that could mediate a fifth force fits into several theoretical frameworks, including string theory and extra-dimensional models. In these theories, the forces of nature are unified into a single, overarching framework that explains how all the fundamental forces are related. String theory, for example, posits that all particles are actually tiny vibrating strings, and these vibrations give rise to the different forces we observe. In this context, a fifth force could arise from the interactions of these strings in higher dimensional space, beyond the familiar 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. Such a force could operate on very small scales, and its effects might be detectable only through experiments like Muon G2 and LHCb. Another connection between quantum mechanics and the potential fifth force lies in the concept of virtual particles. In quantum mechanics, the vacuum is not empty space, but is instead filled with fleeting particles that pop in and out of existence. These virtual particles can have real effects on the behavior of other particles, influencing their interactions in ways that are difficult to predict. It is possible that a new force could be mediated by virtual particles that interact with known particles in subtle ways, leading to the anomalies observed in experiments like Muon G2. This idea aligns with the concept of the dark photon mentioned earlier, where the fifth force could be mediated by a new type of particle that interacts with dark matter and normal matter in a way that we have not yet fully detected. The role of quantum mechanics in the search for a fifth force is not limited to the discovery of new particles. It also offers a framework for understanding the subtle effects that such a force might have on the particles we already know. For example, in the case of the muon anomaly observed in the Muon G2 experiment, quantum mechanics tells us that the magnetic moment of the muon is influenced not just by the electromagnetic force, but also by other quantum effects, such as the interactions between virtual particles. If a new force is present, it could manifest through these interactions, leading to the observed deviation from the standard model predictions. Quantum mechanics also provides a way to think about the scale at which a potential fifth force might operate. Forces like electromagnetism and the strong and weak nuclear forces act on very different scales. Electromagnetism operates on the scale of atoms and molecules, while the strong and weak forces operate on the scale of subatomic particles. If a fifth force exists, it could operate on a different scale, perhaps interacting only with certain particles like muons or B-mesons, as seen in the anomalies in the Muon G2 and LHCb experiments. The search for a fifth force through the lens of quantum mechanics is, in many ways, an exploration of the unknown. It is an attempt to push the boundaries of our understanding of the universe by exploring new interactions, new particles, and new fields that exist beyond the scope of the standard model. If a fifth force is real, it could reveal new dimensions of reality, providing insights into the connections between the known forces and the hidden mysteries of the universe, including dark matter, dark energy, and even the nature of space and time itself. As we continue to probe the anomalies observed in particle physics experiments, we must remember that quantum mechanics remains one of the most powerful tools we have to explore these questions. The theories of a fifth force rooted in quantum mechanics may one day lead us to a deeper understanding of the fundamental nature of reality, offering answers to questions that have puzzled scientists for centuries. The search for a fifth force, while exciting and full of potential, is far from simple. The anomalies observed in experiments like Muon G2 and LHCb have certainly raised the possibility of a new force, one that could alter our understanding of the universe. However, confirming the existence of a fifth force is a monumental challenge. In the world of particle physics, where precision is paramount and the smallest deviations can lead to groundbreaking discoveries, proving the presence of a new force requires overcoming significant scientific and technical hurdles. The first challenge in confirming the fifth force lies in the very nature of the anomalies themselves. The discrepancies observed in experiments like Muon G2, where the muon's magnetic moment deviates slightly from theoretical predictions, and LHCb, where B-mesons behave in unexpected ways, are subtle. These anomalies are small, and while statistically significant, they don't represent large-scale deviations that would immediately point to a new force. In fact, many of the results are in the realm of precision measurements, meaning that they are based on tiny, seemingly inconsequential differences that could easily be explained by errors or by factors not fully accounted for in the models. In particle physics, even small experimental uncertainties can lead to false positives. The history of science is filled with examples where early results seem to hint at new phenomena, only for subsequent investigations to show that these results were due to overlooked factors, measurement errors, or misunderstandings of existing physics. For instance, some early measurements in the Muon G2 experiment were affected by uncertainties in the magnetic field strength and the precision of the timing measurements. While these uncertainties have been addressed over time, they highlight the difficulty in isolating and verifying the presence of new forces. The precision required to observe the smallest deviations is one of the main reasons why confirming a fifth force is so difficult. The Muon G2 experiment, for example, is designed to measure the Moon's behaviour with an accuracy of several parts per million, an extraordinary level of precision. Yet even such meticulous experiments are vulnerable to sources of error that can influence the results. Whether it's the magnetic environment, the exact timing of particle decay, or subtle quantum effects that haven't been fully modelled, every small factor must be accounted for to ensure the results are reliable. Moreover, the discovery of a fifth force would not be as simple as observing a single anomaly and concluding that it's caused by an unknown interaction. Physics experiments often yield results that are consistent with multiple interpretations. A small deviation from expected behaviour could be the result of a new force, but it could also be the result of an unknown factor in the experimental setup, a new particle that behaves in ways we didn't anticipate, or an effect that hasn't been properly modelled yet. For example, the strange behaviour of B mesons observed at LHCb could be caused by new particles that interact differently with the weak nuclear force, rather than a new force altogether. Similarly, the muon's anomalous magnetic moment could be due to the influence of yet undiscovered particles that interact with the muon via the electromagnetic force, rather than an entirely new force. To confirm the existence of a fifth force, physicists would need to gather a vast amount of consistent data from multiple sources and experiments. One experiment is rarely enough to prove the existence of a new phenomenon in physics. For example, in the case of the Higgs boson, it took years of experiments at CERN's Large Hadron Collider to gather enough evidence to confirm the particle's existence. Even then, the discovery was not an immediate, unquestioned truth. It took time for the scientific community to fully accept and verify the results. Another challenge in confirming a fifth force is that the new force might be incredibly weak, with effects that are difficult to detect. If the fifth force interacts only with certain types of particles, such as muons or B mesons, it could be nearly impossible to detect it in everyday phenomena. In fact, the reason why the anomalies in Muon G2 and LHCb are so intriguing is that they suggest that the fifth force, if it exists, might only manifest in very specific interactions. It could be a force that acts on a very small scale, influencing subatomic particles without leaving a trace in the macroscopic world. This makes it even harder to detect, as most of our experiments are designed to probe the behaviour of larger systems or more common particles. Additionally, the potential existence of a fifth force raises the question of whether it operates only in very specific conditions. Would this force act only at high energies, as is the case with the strong and weak nuclear forces? Or could it be a force that operates at everyday scales, influencing objects we can easily observe and measure? If the fifth force is similar to electromagnetism or gravity, it might have much broader effects. If it is as weak as some of the theories suggest, its influence might only be noticeable under the right conditions, such as in the extreme environments of particle accelerators or in the rarefied conditions of certain particle interactions. Even if we were to detect a new force, confirming its precise nature would require more than just detecting its effects. Scientists would need to develop a full theoretical framework that explains how the force fits into our existing understanding of physics. The introduction of a fifth force would require reworking the standard model of particle physics, and that is no small task. The standard model has been developed and refined over many decades, and it is incredibly well tested. Adding a new force would require not only understanding how it interacts with the known particles and forces, but also determining how it affects the fundamental structure of matter and space. This would be a complex and lengthy process, requiring new mathematical models, experimental data, and collaboration across multiple fields of physics. The search for a fifth force also faces the challenge of competition from alternative explanations. There are many possible ways to explain the anomalies seen in Muon G2 and LHCb without invoking a new force. Some scientists have suggested that the observed deviations might be the result of unknown particles or interactions that don't require a fifth force. For example, some models propose that the anomalies could be explained by the existence of new types of particles that interact with muons or B-mesons in ways that we don't yet understand, but that don't require the introduction of a new force. These models would be simpler to test and might offer an easier explanation for the observed data. Despite these challenges, the potential discovery of a fifth force is one of the most exciting prospects in physics. If the anomalies observed in the Muon G2 and LHCb experiments are confirmed, they could represent a breakthrough that would change our understanding of the fundamental forces of nature. But to confirm this discovery, physicists will need to gather more data, refine their experiments, and develop new theories that explain how this force fits into the broader picture of physics. The path to confirming a fifth force is complex and fraught with difficulties, but the potential rewards are immense. If a new force is discovered, it could unlock answers to some of the most profound questions in science, including the nature of dark matter, dark energy, and the unification of the fundamental forces. As we continue to explore the universe at the smallest scales, the search for a fifth force remains a crucial part of the quest to understand the fundamental nature of reality. The road ahead may be long, but the possibilities are vast, and the potential discoveries could reshape our understanding of the universe forever. The Muon G2 experiment, with its subtle yet profound implications, has already proven to be a cornerstone in the exploration of potential new forces in physics. As we've seen, the experiment has revealed a deviation in the muon's magnetic moment, a discrepancy from what the standard model would predict, which has spurred a flurry of excitement within the scientific community. However, while the initial results are intriguing, the future of the Muon G2 experiment is just as crucial to our understanding of whether we are on the verge of discovering a fifth force or unveiling entirely new layers of physics. The ongoing work at Fermilab, where the Muon G2 experiment is based, promises to provide more data, refine current measurements, and test the validity of the anomalies we've already observed. First, let's briefly recap what makes the Muon G2 experiment so significant. The goal of the experiment is to measure the magnetic moment of the muon with extraordinary precision. In quantum mechanics, the magnetic moment of particles like the muon is influenced by the electromagnetic force, but it can also be affected by other quantum effects, such as interactions with virtual particles in the quantum vacuum. The standard model provides precise predictions for the muon's magnetic moment, but the results from the Muon G2 experiment, as we've seen, showed a slight deviation from these predictions. This discrepancy has been interpreted as a potential sign that the muon is interacting with an unknown force, leading some scientists to speculate that this could point to a fifth force beyond the four known fundamental forces. But these results, while promising, are not conclusive. There are still many questions to answer before we can definitively confirm that the anomaly represents a new force. The first step is to gather more data. The precision required to measure the muon's magnetic moment to the degree needed for this experiment is staggering, but even small uncertainties can lead to significant changes in interpretation. Since the anomaly is subtle, even slight adjustments to the experimental setup or new insights into the sources of error could either reinforce or challenge the idea of a fifth force. Fermilab's Muon G2 experiment is currently in the process of running multiple cycles of measurements to further refine the results. The precision of the measurements is crucial, and as the data collection continues, scientists will be able to improve the accuracy of the magnetic moment measurements. it's important to note that experiments of this magnitude are not only about getting more data, they're also about refining the methods used to eliminate potential sources of error. The experimental setup itself is incredibly sophisticated, with muons being injected into a large circular storage ring where they are subjected to a carefully controlled magnetic field. The muons then precess, or wobble, in response to this field, and the rate of precession is used to calculate their magnetic moment. Any small variations in the magnetic field, the muon injection process, or even in the way muons interact with other particles could influence the final results. Another important aspect of the future of the Muon G2 experiment is the development of new theoretical models. The deviation in the muon's magnetic moment, while intriguing, does not yet provide a clear path forward. The possibility that the anomaly is due to an entirely new force is an exciting one, but before we can claim that with certainty, scientists need to develop models that can explain the data in a way that fits within the larger framework of particle physics. The current models based on the standard model of particle physics do not predict the anomaly we are seeing, so new theories must be considered. These models will not only account for the muon anomaly, but will also need to explain why we haven't seen similar effects in other experiments. For example, if the muon's magnetic moment is being influenced by a new force, why aren't similar deviations observed in other particles such as electrons or tau leptons? One possibility is that the new force could only affect certain particles or types of interactions. This might explain why we see anomalies in the muon, which is a heavier version of the electron but not in the electron itself. Alternatively, the new force could be incredibly weak, only detectable in certain specific conditions or experimental setups, which would make it difficult to observe in other experiments. Understanding how this potential new force interacts with different particles and forces is one of the key challenges facing the scientific community as the Muon G2 experiment moves forward. The future of the experiment is also dependent on advancements in technology and the development of even more sensitive detection methods. The apparatus used to measure the muon's magnetic moment is already one of the most advanced in the world, but as technology improves, scientists will be able to make even more precise measurements. For example, advancements in cryogenics, the study of extremely low temperatures, have allowed the experiment to reach the necessary conditions for studying muons in great detail. Further innovations in data collection and analysis techniques will also play a crucial role in reducing errors and improving the accuracy of the results. Beyond the measurements themselves, the future of the Muon G2 experiment will also involve collaborations with other experiments and theoretical physicists. The results of this experiment are not isolated. They have the potential to interact with other areas of research in particle physics, such as those studying dark matter, dark energy, and quantum field theory. If the Muon G2 anomaly is indeed the result of a new force, it would likely have connections to these other unexplained phenomena. For example, some theories propose that the fifth force could be linked to dark matter, suggesting that muons and other particles might interact with dark matter in ways that we have yet to detect. By working with other experiments that are focused on dark matter detection and the search for other anomalies, scientists can begin to build a more complete picture of what might be happening. In addition to these collaborations, the future of the Muon G2 experiment will depend on the findings of other experiments at facilities like CERN's Large Hadron Collider. The LHC, which has already provided crucial insights into the nature of particle interactions and the discovery of the Higgs boson, may provide complementary data that can help to verify or refute the findings of the Muon G2 experiment. The LHCb experiment, which has observed anomalies in the behavior of B mesons, could also be key in confirming whether these anomalies are related to a fifth force. Another important factor is the role of international collaboration in the future of the Muon G2 experiment. Particle physics research, especially at the scale of the Muon G2 experiment, requires significant resources and expertise from scientists around the world. The collaboration of physicists from multiple countries, each bringing their own specialized knowledge and skills, is essential for tackling the challenges presented by such complex experiments. The exchange of ideas and data between international research teams ensures that the experiment remains at the cutting edge of scientific discovery. Finally, if the Muon G2 experiment successfully confirms the existence of a fifth force, it would not only transform our understanding of particle physics, but also open up new avenues of research into the very nature of the universe. The implications for technology, cosmology, and fundamental physics would be profound, potentially leading to a unification of the forces of nature or a new theory of everything. But before such conclusions can be drawn, the experiment must continue to gather data, refine measurements, and develop theoretical models to explain the results. The journey is far from over, and the next few years will likely be critical in determining whether the anomaly observed in the muon's magnetic moment is indeed the first sign of a fifth force, or a subtle misinterpretation of existing physics. In short, the future of the Muon G2 experiment is filled with potential. The road ahead may be long and fraught with challenges, but the rewards for confirming the existence of a new force would be nothing short of transformative. As we continue to explore the universe at the smallest scales, the experiment will remain a key part of the ongoing quest to unravel the deepest mysteries of the cosmos. The LHCb experiment at CERN is one of the most important experiments currently underway in the quest to uncover new forces and particles that could alter our understanding of the universe. As we've discussed earlier, the LHCb has observed anomalies in the behaviour of B mesons, subatomic particles that are made up of a bottom quark and another type of quark, such as an up or down quark. These anomalies have raised the possibility that there might be a fifth force at play, one that operates in a way that the standard model of particle physics cannot explain. But the discovery of such a force is not something that can be confirmed with a single experiment. The LHCb, along with other experiments at CERN and around the world, is continuing to investigate these anomalies, gather more data, and refine our understanding of what might be happening. The LHCb experiment is part of the larger Large Hadron Collider, LHC, at CERN, which is the world's largest and most powerful particle accelerator. The LHCb is specifically designed to study the behaviour of B mesons and other particles that are involved in weak force interactions. The weak force, which is responsible for processes like beta decay, is one of the four fundamental forces in nature, but it is not fully understood, especially when it comes to the behaviour of particles like B mesons. These particles are unstable, decaying rapidly into other particles, but their interactions provide valuable insight into the weak force and could reveal new physics. The anomalies observed at LHCb have been particularly striking because they seem to suggest that B mesons are decaying in ways that contradict the predictions of the standard model. Specifically, the data has shown deviations in how B mesons decay into leptons, particularly in their interactions with muons and electrons. In the standard model, leptons should interact with the weak force in the same way, regardless of whether they are electrons, muons, or tau particles. However, the LHCb results suggest that muons and electrons are not behaving identically in these decays, pointing to a possible violation of the principle of lepton flavor universality. This has raised the possibility that there is an unknown force interacting with B mesons, potentially hinting at a fifth force that acts differently on different particles. So, what exactly is being done to investigate these anomalies further, and what do we expect to find? The first step in investigating these findings is to gather more data. The anomalies observed so far, while statistically significant, are not yet definitive. They are subtle differences from the expected results, and in the world of particle physics, even small uncertainties in measurements can lead to a range of possible explanations. To confirm the presence of a new force or particle, scientists need to collect much more data to ensure that the anomalies are not the result of experimental error or incomplete understanding of existing interactions. The LHCb experiment is currently running additional rounds of data collection to refine the measurements and confirm whether the anomalies persist under different conditions. The LHC itself is a massive particle accelerator that collides protons and other particles at extremely high energies, and the LHCb detector is designed to capture the resulting particle decays and interactions with high precision. By examining a greater number of B meson decays, researchers hope to increase the statistical significance of the anomalies and rule out any alternative explanations that might be responsible for the observed behaviour. In addition to gathering more data, physicists are also working to improve the experimental methods used to analyse the behaviour of B mesons. Particle detectors like those used in the LHCb experiment are incredibly complex, and even the smallest uncertainties in the measurements can lead to discrepancies. The LHCb collaboration is continually refining its detectors, improving their sensitivity and reducing the noise that could interfere with the results. Advances in data analysis techniques are also crucial as scientists work to sift through massive amounts of experimental data to isolate the signals that could point to a new force or particle. Another key aspect of the investigation is the theoretical work being done to interpret the anomalies. While the data from LHCb suggests the possibility of a fifth force, there are many potential theoretical explanations for what might be happening. For example, the behaviour of B mesons could be due to the influence of new particles that interact with the weak force, or it could be the result of a previously unknown interaction between particles. To understand what the data is telling us, scientists need to develop new models that go beyond the standard model and explore how these anomalies could fit into a broader theory of particle physics. Theoretical models that involve extra dimensions or dark matter are two possibilities that have been proposed to explain the LHCb anomalies. Some scientists speculate that the new force could be tied to the hidden dimensions predicted by string theory, which suggests that the universe may have more than the familiar 3 dimensions of space and 1 dimension of time. If these extra dimensions exist, they could be influencing the behaviour of particles like B mesons in ways that the standard model does not account for. Similarly, the idea that the fifth force could be related to dark matter has gained traction. Dark matter is a mysterious substance that makes up a large portion of the universe's mass, but does not interact with light or other forms of electromagnetic radiation. If the anomalies in B mesons are linked to dark matter, it could represent a significant breakthrough in our understanding of both particle physics and cosmology. Beyond these theoretical models, the LHCb experiment is also working closely with other experiments at CERN and around the world to verify the results. Particle physics is a highly collaborative field, and results from one experiment are often cross-checked against those from others. The Muon G2 experiment, which has observed similar anomalies in the behaviour of muons, is an important source of complementary data. If the anomalies in both experiments are connected, it would strengthen the case for a new force and provide a more comprehensive understanding of how it operates. Similarly, the ongoing work at other experiments like ATLAS and CMS at the LHC could provide additional insights into the possible existence of a fifth force. Ultimately, the future of the LHCb experiment and the investigation of these anomalies is a race against time. With each passing year, more data is collected, new models are developed, and the scientific community's understanding of the problem deepens. The anomalies in B meson decays are not just small discrepancies, they represent a window into something that could profoundly change our understanding of the universe. If these anomalies are confirmed as the result of a new force, it would be one of the most important discoveries in the history of physics, offering answers to some of the biggest questions about the fundamental nature of reality. While it's impossible to predict exactly what the future holds, it's clear that the LHCb experiment is poised to play a central role in the ongoing investigation of these anomalies. Whether the results eventually point to the discovery of a fifth force or lead us in an entirely new direction, the research being conducted today will shape the future of particle physics for years to come. And, as with many of the great discoveries in science, the journey itself will be just as important as the destination. The question of whether the potential discovery of a fifth force will change our understanding of the universe is profound, and its implications could ripple through nearly every aspect of modern physics. For decades, the standard model of particle physics has served as our best framework for understanding the fundamental forces and particles that make up the universe. It has explained everything from the behavior of electrons in atoms to the interactions that hold atomic nuclei together. Yet, despite its success, the Standard Model is incomplete. It doesn't account for gravity, it fails to explain the nature of dark matter and dark energy, and it leaves several unanswered questions about the fundamental nature of reality. The discovery of a fifth force, whether it's related to dark matter, dark energy, or something else entirely, could offer answers to these gaps and reshape our understanding of the cosmos in ways we cannot yet fully imagine. The very possibility of a fifth force challenges the foundational concepts we've held in physics for nearly a century. The forces we currently understand, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are already strange enough. Each of them operates on different scales and in different ways, but they are united by one thing. They are the fundamental interactions that shape the behavior of matter and energy in the universe. Gravity is the force that holds galaxies together and governs the motion of celestial bodies. Electromagnetism governs the interactions between charged particles and is responsible for everything from electricity to magnetism. The strong force binds quarks together to form protons and neutrons, while the weak force governs processes like beta decay and the fusion reactions in stars. But these four forces have limitations. Gravity, for instance, is not included in the Standard Model. While it governs large-scale structures like planets and galaxies, it behaves differently from the other forces at the quantum level, where quantum mechanics rules. Dark matter and dark energy, which make up roughly 95% of the universe's mass and energy, cannot be explained by any of the four known forces. Their presence is inferred from their gravitational effects, but their true nature remains one of the greatest mysteries in modern science. The potential discovery of a fifth force could help solve these mysteries. If the anomalies observed in experiments like Muon G2 and LHCb are indeed the result of a new force, it would open up an entirely new chapter in physics. The implications for our understanding of the universe are profound. For one, such a discovery could help bridge the gap between quantum mechanics and general relativity, two of the most successful but fundamentally incompatible theories in physics. The search for a unified theory, one that explains both the quantum world of subatomic particles and the macroscopic world of gravity, has been a driving force in theoretical physics for decades. A fifth force, if proven to exist, could be the key that unlocks this unification, helping scientists develop a framework that integrates all of the fundamental forces. Moreover, a new force could help explain the nature of dark matter and dark energy, two of the most perplexing and elusive phenomena in the universe. Dark matter, which makes up about 27% of the universe's mass, doesn't interact with light, making it invisible to traditional observation methods. Yet its presence is inferred from its gravitational effects on visible matter. If the fifth force is related to dark matter, it could provide the missing link that allows us to directly detect dark matter particles, giving us a clearer picture of the universe's hidden mass. Similarly, dark energy, which is thought to make up about 68% of the universe's energy, is responsible for the accelerated expansion of the cosmos. It has been observed through its effects on the large-scale structure of the universe, but its nature is still unknown. Some theories suggest that dark energy could be tied to the fifth force, possibly offering a new way of understanding the fundamental forces that drive the universe's expansion. If this is the case, the discovery of a fifth force could revolutionize cosmology, helping scientists unlock the secrets of the universe's birth, evolution, and ultimate fate. The discovery of a fifth force would not only expand our understanding of the cosmos, but would also impact our perception of the very nature of reality itself. It would imply that the universe is far more complex and interconnected than we previously thought, with hidden dimensions and forces shaping the behavior of particles in ways we can barely imagine. The discovery would challenge the assumptions that have guided physics for centuries, forcing scientists to rethink how the fundamental forces of nature operate and how they are connected. For example, some theories propose that the fifth force could be related to the existence of extra dimensions. The idea that there might be more than the familiar 3 dimensions of space and one of time is a central feature of string theory and other higher dimensional models. If a new force is mediated by particles that interact with these extra dimensions, it would imply that the universe has hidden aspects that are completely beyond our direct perception. This would profoundly alter our conception of space, time, and reality itself. Another possibility is that the fifth force could be tied to supersymmetry, a theoretical framework that posits that every particle in the Standard Model has a corresponding superpartner particle. If supersymmetry is correct, the discovery of a fifth force could provide the first direct evidence of supersymmetric particles, opening the door to a whole new class of particles and interactions that have never been observed before. This would not only expand our knowledge of particle physics, but could also have practical implications for fields like energy generation, materials science, and even computing. In addition to these fundamental shifts in our understanding of physics, the discovery of a fifth force would have a broader impact on science and technology as a whole. New discoveries in physics often lead to technological advances that change the way we live. For example, the development of quantum mechanics led to the creation of technologies like computers, lasers, and MRI machines. A new understanding of the fundamental forces could lead to breakthroughs in areas like energy, space exploration, and materials science. If the fifth force is tied to dark matter, for instance, it could open up new avenues for detecting and harnessing dark matter, potentially leading to entirely new energy sources or propulsion methods. The discovery of a fifth force could also shift the focus of particle physics and cosmology in new directions. For decades, the search for the Higgs boson and the study of the Standard Model have been at the forefront of particle physics research. But a new force would shift the focus of scientific inquiry, leading to an entirely new set of questions and challenges. It would inspire new experiments, new theoretical models, and new collaborations as scientists across the world work together to unravel the implications of this discovery. And despite the excitement and potential for discovery, it's important to recognize that the journey toward confirming the existence of a fifth force is not guaranteed. The anomalies observed in Muon G2 and LHCb are intriguing, but they are not conclusive proof of a new force. There are still many possible explanations for the deviations we're seeing, and it will take time and further experiments to confirm whether these anomalies are the result of a new force or if they can be explained by some other unknown factor. However, the possibility remains that these anomalies point to something truly revolutionary, and if that turns out to be the case, it would fundamentally change the way we view the universe. In conclusion, the potential discovery of a fifth force represents a pivotal moment in the history of science. It could answer some of the most profound questions about the universe, questions about dark matter, dark energy, and the unification of the forces of nature. It could reshape our understanding of space, time, and reality itself, and open up new frontiers in physics, cosmology, and technology. As scientists continue to probe the anomalies observed in the Muon G2 and LHCb experiments, the future of physics looks brighter than ever, with the possibility of uncovering a new force that could change everything. Dark matter is one of the most enigmatic and profound mysteries in modern science. It is a substance that, while invisible and undetectable by direct observation, seems to exert a powerful influence on the universe, shaping the behavior of galaxies, clusters of galaxies, and even the large-scale structure of the cosmos. Despite making up about 27% of the universe's total mass, dark matter remains a complete mystery in terms of what it actually is. We cannot see it, we cannot touch it, and we cannot directly measure it. Yet its presence is undeniable, and the search for dark matter has become one of the most urgent quests in contemporary physics and cosmology. The story of dark matter begins with observations that did not fit with our expectations based on visible matter alone. In the 1930s, the Swiss astronomer Fritz Zwicky noticed something strange when studying the Coma galaxy cluster. Based on the velocities of galaxies within the cluster, he calculated that the gravitational pull of visible matter, such as stars, was not sufficient to hold the cluster together. According to his calculations, the galaxies should have flown apart, but they didn't. Something else must have been present, something invisible, exerting additional gravitational influence to bind the cluster together. Zwicky's observation led to the first suggestion of dark matter, although the term itself did not come into widespread use until later. In the decades that followed, further evidence for dark matter accumulated. For example, the rotation curves of galaxies showed discrepancies. Stars at the outer edges of galaxies were orbiting much faster than would be expected if only the visible matter, such as stars and gas, was present. According to Newtonian mechanics, stars on the edges of galaxies should be moving slower than those near the centre, but this was not the case. Instead, the stars were orbiting at much higher speeds, suggesting that an unseen mass was providing additional gravitational pull. The most compelling evidence for dark matter, however, comes from its gravitational effects on the large-scale structure of the universe. Observations of the cosmic microwave background, CMB, radiation, the afterglow of the Big Bang, show subtle patterns that can only be explained if dark matter is present. Dark matter influences the way matter clumps together in the early universe, affecting the formation of galaxies and other cosmic structures. Without dark matter, the universe as we know it would look very different, and the galaxies would not have formed in the same way. Despite this overwhelming evidence for its existence, dark matter remains an elusive mystery. Scientists have ruled out the possibility that dark matter is composed of ordinary visible matter, such as stars or planets, because it does not emit, absorb or reflect light, making it invisible to traditional detection methods. It also does not interact with electromagnetic forces in the way that regular matter does. This is why dark matter is often described as dark, because it does not interact with light, and thus cannot be seen directly with telescopes or other observational tools. So what is dark matter? What are these elusive particles that are thought to make up the majority of the universe's mass? While many possibilities have been proposed, we have yet to identify dark matter with certainty. The leading candidates for dark matter are particles that do not interact with light or other forms of electromagnetic radiation. These particles would have to be very weakly interacting with regular matter, which is why they remain so difficult to detect. One of the most widely studied candidates for dark matter is the weakly interacting massive particle, WIMP. WIMPs are hypothetical particles that interact only via the weak nuclear force and gravity, making them nearly invisible to traditional detection methods. If WIMPs exist, they would be abundant in the universe, and their gravitational effects could explain the observed phenomena, such as the rotation curves of galaxies. However, despite extensive efforts to detect WIMPs, no direct evidence has yet been found. Experiments like the Large Hadron Collider, LHC, and underground detectors are still actively searching for signs of WIMPs, but so far the search has yielded no conclusive results. Another possibility for dark matter is the axion, a hypothetical particle that is even lighter than the WIMP. Axions are proposed as a solution to a long-standing problem in particle physics, known as the strong CP problem. Like WIMPs, axions would interact only weakly with regular matter, making them difficult to detect. However, unlike WIMPs, axions are predicted to have very low masses, and they could potentially be detected through their interaction with electromagnetic fields. Research on axions is ongoing, and scientists are hoping that experiments will eventually provide evidence for their existence. In addition to these hypothetical particles, some theories suggest that dark matter might be composed of more exotic forms of matter. For example, primordial black holes, which are black holes formed in the early universe, have been proposed as a potential candidate for dark matter. These black holes would be small and difficult to detect, but their gravitational effects could explain the observed behavior of galaxies. However, this idea is still controversial, and more evidence is needed to determine whether primordial black holes could make up dark matter. Despite the many theories, the true nature of dark matter remains one of the biggest open questions in physics. The search for dark matter is not just about discovering a new particle, it's also about unlocking the mysteries of the universe. Dark matter holds the key to understanding the fundamental structure of the cosmos and the forces that govern its evolution. It is believed to be responsible for much of the structure of the universe, from galaxies to the cosmic web that spans the entire observable universe. Understanding dark matter could help scientists answer some of the most profound questions about the nature of space, time, and the forces that govern the universe. But what does dark matter have to do with the potential discovery of a fifth force? The link between dark matter and the fifth force is becoming increasingly apparent. If the anomalies observed in experiments like Muon G2 and LHCb are indeed pointing to a new force, it is possible that this force is related to dark matter. For example, some theories propose that dark matter particles could interact with ordinary matter via a previously unknown force, potentially explaining the deviations seen in the muon's magnetic moment and the strange behavior of B mesons. If such a force exists, it could open up new ways to detect dark matter directly, leading to breakthroughs in our understanding of this mysterious substance. The search for dark matter and the search for a fifth force are closely related, and the potential discovery of a new force could provide the missing link in our understanding of dark matter. By studying the anomalies in particle physics experiments, scientists are not only probing the nature of the fifth force, but are also exploring the deeper connections between ordinary matter and the dark matter that dominates the universe. If dark matter is indeed linked to a new force, it could provide a more complete picture of the universe's mass and energy, one that includes both the visible and invisible components that make up the cosmos. In conclusion, dark matter is one of the greatest mysteries of modern science. It is a substance that has been detected through its gravitational effects, but remains invisible and undetectable through traditional means. Despite numerous efforts to detect dark matter directly, its true nature remains elusive. However, the potential discovery of a fifth force could provide the key to unlocking this mystery. By exploring the possibility that dark matter is connected to a new force, scientists may one day be able to understand its true nature, and in doing so, they may uncover one of the most profound revelations in the history of science. The search for a fifth force is not just a quest to uncover a new interaction in the universe, it's an exploration of the very fabric of reality itself. The anomalies observed in experiments like Muon G2 and LHCb have opened a door to the possibility of a hidden force that could change everything we know about the universe. If confirmed, the discovery of a fifth force would represent a monumental shift in our understanding of physics, offering insights into dark matter, dark energy, and the unification of the forces that govern the universe. For decades, the standard model of particle physics has served as the cornerstone of our understanding of the fundamental forces. It has successfully explained the behavior of particles, the interactions between them, and the forces that hold the fabric of the cosmos together. Yet, despite its success, the standard model is incomplete. It does not account for gravity, the most familiar of the forces. It cannot explain the nature of dark matter or dark energy, which together make up nearly 95% of the universe's mass and energy. And it leaves several key questions about the nature of particles, forces, and the very structure of space-time unanswered. The discovery of a fifth force would not just fill in the gaps in the standard model, it could fundamentally alter the way we understand the universe, providing the missing pieces of the puzzle that have eluded physicists for so long. The implications of a fifth force extend beyond just particle physics. If such a force is real, it could unify the forces of nature in ways we have not yet imagined. It could bridge the gap between quantum mechanics and general relativity, two theories that, while incredibly successful in their respective domains, have never been reconciled into a single theory of everything. A new force could provide the framework needed to unify these two pillars of physics, helping us understand both the smallest particles and the largest cosmic structures in a single, coherent framework. But the potential impact of this discovery goes even further. A fifth force could explain the mysteries of dark matter and dark energy, two of the most perplexing phenomena in the universe. Dark matter, which makes up a significant portion of the universe's mass, interacts only gravitationally, leaving no trace of its presence except for its effects on visible matter. If the fifth force is related to dark matter, it could help us detect this invisible substance directly and unlock the secrets of the universe's hidden mass. Similarly, dark energy, the force behind the accelerated expansion of the universe, could be tied to this new force, providing a deeper understanding of the fundamental forces that shape the cosmos. The discovery of a fifth force would also challenge our most basic assumptions about space and time. It could point to the existence of hidden dimensions, new particles, and interactions that we cannot currently perceive, reshaping our understanding of the very structure of the universe. It could reveal connections between the visible and invisible components of the universe, showing us a deeper, more interconnected reality. If these anomalies are indeed the result of a new force, it would be the beginning of a new chapter in the history of physics, one that could forever change the way we perceive the universe and our place within it. Yet, despite the excitement and potential, we must also acknowledge the uncertainties that lie ahead. The road to confirming the existence of a fifth force is not straightforward. The anomalies observed in Muon G2 and LHCb are still in the early stages of investigation, and much more data is needed to verify their significance. There are also many possible explanations for these anomalies that do not involve a new force, such as the influence of unknown particles or interactions. The scientific community must continue to approach these results with caution, refining experimental techniques, improving theoretical models, and gathering more data to ensure that any new discovery is based on solid evidence. As scientists continue to explore the possibilities of a fifth force, the implications for the future of physics are immense. The search for new forces, new particles, and new interactions is a journey that could take us into uncharted territory, revealing hidden dimensions and uncovering aspects of the universe that have been concealed from our view. It is a journey that will require collaboration across disciplines, with physicists, cosmologists, and other scientists working together to unravel the mysteries of the cosmos. If a fifth force is discovered, it will not be just a breakthrough for physics, it will be a breakthrough for humanity's understanding of the universe. It will challenge the very foundations of science, prompting us to reconsider our understanding of space, time, and the forces that govern everything from the smallest particles to the largest galaxies. It will inspire a new generation of scientists and spark new questions about the nature of reality. And it will open the door to a future where the universe is seen in a new light, with the potential for discoveries and insights that we can't yet fully fathom. In the end, the search for a fifth force is more than just a scientific endeavour. It is a reminder that the universe is vast, mysterious, and full of wonders yet to be discovered. As we continue to probe the depths of particle physics, cosmology, and the nature of reality itself, we are constantly reminded that science is a never-ending journey of exploration. The path ahead may be uncertain, but it is also filled with potential. The discovery of a fifth force, if it occurs, will mark the beginning of a new era in physics, one that could reshape our understanding of the universe and our place within it.